Just as delta tau was an invariant here, constant, whichever frame of reference I measured delta t and delta x in, this quantity was a constant. Just the same, this quantity mc squared is a constant. So e squared minus pc squared is a constant in any frame of reference. Now, there are some interesting things we can do with that. We've got an equation for the energy. The energy is just mc squared divided by 1 minus v squared over c squared raised to the 1/2 power. And the kinetic energy should just be the total energy minus the rest energy. In this form, I can see that as the speed gets closer and closer to the speed of light, it asymptotes very quickly to infinity. That's just what we talked about at the beginning of the chapter, that as we get closer and closer to the speed of light, the kinetic energy stops going like mv squared and starts to grow very rapidly. Now you may ask, does this, in fact, give the right kinetic energy at low speeds? You could try plugging it into your calculator, but most likely your calculator won't have enough resolution to subtract these two numbers off. Instead, I want to point something out. Suppose we had a function that's 1 plus x to, we'll say, the alpha. That's our function f of x. I can write that as f of 0 plus the first derivative of f, evaluated at 0, times x, plus the second derivative of x, evaluated at 0, divided by 2 times x squared, and I can continue to expand this out. Because I'm expanding around x equals 0, this is known as a Maclaurin series. If I'd expanded around a random x, it would just be a Taylor series. For our purposes, we're just going to focus on these two parts here. Our x is going to be v squared over c squared. And because v is going to be much smaller than c, if I square that quantity, it's going to be pretty negligible. So if this is 1 plus x to the negative 1/2, then f of 0 is equal to 1. F primed is negative 1/2, 1 plus x to the negative 3/2. So f primed of 0 is negative 1/2. Not 1/12, 1/2. So I'm going to plug that in place of 1 plus x to the negative 1/2. So I've got mc squared times 1 minus 1/2 times x, where x is negative v squared over c squared. Notice the negatives cancel, and this is simply equal to the rest energy, mc squared, plus 1/2 mv squared. When I subtract off the rest energy, this term goes away, and my kinetic energy is 1/2 mv squared. Notice the next term will be on the order of this kinetic energy times v squared over c squared. It'll have a v squared over c squared squared in it. At low speeds, that extra term is negligible, whereas at high speeds, we really need to use the entire formula.